So we have this 144 of Leetcode, and the question simply says that you will be given the root of a binary tree, and you need to return the pre-order traversal of the node value. So before getting to the question, first let's look at the time constraints we have. The number of node in a tree can be from the range 0 to 100. So at max, the number of node in a tree can be 10 raised to the power 2. So first let us figure out the maximum time complexity of code that we can design. First we have this time complexity order, right? Now at max our n value can be 10 raised to the power 2, right? Now if we, let's say, if we take this time complexity of O of n cube, put the value of n as 10 raised to the power 2, 10 raised to the power 2 cube will be O of 10 raised to the power 6. And in Leetcode C++, in Leetcode C++, we know for a fact key in 1 second, right? In 1 second, we can have at most 10 raised to the power 6 operations. So even if we go to all the nodes in a tree, it will take we will go to 10 raised to the power 6 nodes, and it will be executed under a second. So this time complexity of O of n cube will actually work under 1 second. So all these time complexities will actually work under 1 second. Now if we make our code run in this time complexity, we will definitely get a TLE. So our maximum time complexity that we can have is O of n cube, right? Now getting to the problem, let's say we have this tree, right? Now in pre-order traversal, we know key first we write the root of the tree, then we write the left, and then we write the right, right? And first writing the root, let's say we will be given this as the root. Now there is a basic thumb line that we need to take in mind. Every single time we move to a new node, right? Every single time we move to a new node of a tree, treat it as the root. Now this will actually actually walk in a bigger tree that we will be given. Let's say, let's iterate over this tree. We are given initially the root of the tree, right? So let's say this is our answer of pre-order traversal, and first we have the root. So according to pre-order traversal, if we have the root, simply write the root. So we wrote the root. Then what we do is we go to the left node, we go to the left child. Now this is our new node, so treat it as the root. Now 2 is our root, so if we have the root, simply write it. Again go to the left, this is your root, so simply write it. Now in the node 4, neither you can go to left or you can go to right, so you simply return back to 2. For 2, treating as the root, you have completed the left iteration of it, the left branch of it. Now you have to execute this right branch, right? Now you have to execute this right branch. Now go to the right branch, right? First you go to the root. For the two node, first you go to the root, then you go to the left branch, then we go to the right branch, right? Then you go to the 5, right? Treat 5 as the new root. Treat 5 as the new root. Now if you treat 5 as the new root, write it down. Then you move to the left, treat it as the root. 6 is the new root. Now you cannot move to the left, neither can you move to the right, so you return back to 5. Now the left iteration for 5 is completed. Now you perform the right iteration. You go to the right node, treat 7 as the root, print out 7. Then 7 does not have any left node, neither has any right node, so you go back to 5. Now for the 5, the left and the right iteration has completed, so you move back to 2. Now again for the 2, the left and the right iteration has completed, so you move back to 1. Now for 1, you have actually completed, let me change the color, you have actually completed the left iteration. For 1, you have completed the left iteration. Now we have key, first you do the root, we wrote the root as 1, we completed the left iteration. This is our root, this was our left iteration that we performed. Now we have to perform the right iteration of 1. Now simply go to the right, treat it as the root, write it down. 3 does not have a left, so we move back to 3. Now for 3, we have completed the left iteration, perform the right iteration. So this is the right side. we move to the right node, treat 8 as the new root, write this down. Can we go to left? Yes, we can go to left. Now treat this as the new root, we write this down. Does 9 has any left or right nodes? No, we don't. We go back to 8. Does 8 has any right node? No, we go back to 8. For 8, we have performed both the left and the right iterations. So we go back to 3. For 3 also we have performed the left and right. We go back to 1. And at last we have performed for the 1, we have performed the root, we have performed the left branch, and we have performed the right branch. So our code executes. So this will be our pre-order traversal. Pre-order traversal. Right now, actually to solve this problem we will use two methods. First will be the recursive way. Now this will be an easy method, and it will have a time complexity of on and space complexity of constant o1. Then we will discuss a difficult method called as iterative way. Now using one stack. Now this is a little difficult one, and this is asked in the interviews, right? Difficult one. Now it has a time complexity of on and space complexity of on. So for the pre-order traversal, let's discuss the recursive way. First, what we do is we go to the root, right? Then what we do, we print the root, right? Then what we do, after printing the root, we move to the left substrate, perform the operation of the left side, and then we go to the right branch, and then our code is over, right? So basically, first we'll be given this as the root, right? The basic idea is that you have a root, you have a left branch, and you have a right branch. Now first you go to root, print it out, go to the left branch. After completing the left branch, return it to root, then go to the right branch. After completing the right branch, return to root, and your iteration will be over for recursive way. Now we'll write the code. Whatever we said, we are going to write it down. Let's say we have a function fx. Now fx will be supplied with the root of the tree, that is 1, right? Root. Let's also maintain a answer, right? Now once you have the root, what do? We wrote the steps, right? You have the root, now you simply print it out. We print the root, right? So we write answer dot pushback root value. Now we push back 1 into the answer, right? Then after printing root, what we do is we move to the left node, the left substrate, the left child of it, right? Once we print 1, then we move to 2 and treat this as the root and perform the same operation here, right? So what we do is we call the same function and pass root left, right? This is what we did, right? For 1, we had the root, we wrote it down, we printed it out, then we move to the left branch of it. So we'll have 2 as our answer. Now after performing the left branch, what we'll do is we'll move to the right branch, right? This is our right branch and this is our left branch. After completing the left branch, we'll move to the right branch and treat 3 as our new root and perform the same operation. So again we will call the function after performing the left branch, right? We'll call for the same function and perform the right branch. So we'll have root right. So what we did was we printed the root, went to the left subtree, and then went to the right subtree, and our function is over. Now this is our function, but there is a so this is a recursive function, but we don't have a base case. Now we need to write a base case. Let's say we went to 1, printed out 1, went to 2, printed out 2, then we moved to the left, went to 4, printed out 4. Now 4 does not have any left, neither it has any right, so it has null, right? What we have to do is once we see null, we need to return back, right? Every single time we see null, we need to return back. 5 will have null, 6 will have null, trees left will have null. Every single time we'll see null, we'll need to return back. So this will be our base condition. If the root is equal to null, if the root is equal to null, simply return, right? That is what we are doing. After 4 we went to null, treated null as the root, and we'll simply return back to 4. Then went to right substrate, where saw it as null, treated it as a root, and returned back to 4, and then again return back to 2. Completed the left substrate, then complete the right substrate, again return back. This is what we did, right? See, there are two return statements. See, this is our base condition. Whenever you see a null, simply return. And whenever you complete the left substrate and the right substrate, again return, right? When for 4 we had null in both the case, the left and right was null, so we returned. And for 2 the left substrate was completed and the right substrate was completed, so we returned. These are the two return conditions we'll have. So this code will work under a time complexity of O(n). Why? Because we have to at least once visit each of the node to print it out, and we'll have a space complexity of O(1) because we are not consuming any extra space. So now we are going to discuss the iterative way of pre-order traversal, and this is the most important question and asked in interviews, right? Now we had this sequence in recursion, in the recursive way, right? We go to root, print out the root, go to the left branch, complete it, return back, and go to the right branch, right? Let's take an example of a tree. Let's say we have a tree something like this: 1 2 3 4 5 4 5 and let's say 6. Now this is a tree that we are given. Now this is the root that will be provided with. Now we will use the iterative way. Iterative way simply means that either we'll use a while loop or a for loop to write all the nodes. Now what will be the answer? Actually the answer will be get to the 1, then go to the left node, write the 2, then get to the again left 6, then go to the right, which is 3, right's left, that is 4, and then to 5, right? This should be our answer. Now using iterative way, what we can use is that we can first let us write it. Now there is a big problem in this iterative. The problem is that from the parent node, once you get to the child node, you can never get back, right? Let's say we are at node 1, right? So we are at node 1, and so once we get to node 2 and complete this left branch, this is the left branch and this is the right branch, right? Once we go to 2, we can never get back to 1. It's like a linked list. In a single linked list, there is no way you can get back, so you can never get access to the right branch of the code. Neither you can get access to root once you move to child. So for this reason, in iterative way, you have to use an intermediate memory element. Now the intermediate memory element could be a stack, could be a queue, could be a vector, or could be any other data structure. But the implementation of queue and vectors are very, very complex. Stack has the most simplest push and pop operation which could be used here. Now let's say we will have the tree, right? We will have the tree, and we will take the input from the tree, push it into the memory element. Our memory element here is stack, and from the stack we'll push it into our answer vector, right? This is our final vector that we need to return. Now I'll tell you exactly how to implement stack. 1 2 3 4 5 and 6, right? And this was the root that was given. Now what is the problem that we are solving is that once we are at the node 2, we cannot get back, so we need a memory element, so we create a stack. Now I'll explain you with an example. This is our stack and this is the answer that we are given. Now first we are at the node 1, so simply push 1 into the stack. The flow is this way, right? From the tree you write into the stack, and from the stack you write into the answer vector. Whenever you pop out of a stack, simply do what? Push the children of 1 into the stack in the reverse way. We had root, left, and right. So first push the right into the stack, then the left children. So once right children is 3 gets pushed in and 2 gets pushed in. So now get to the stack, see the top element, pop it out, write it in the answer, and again push the children of 2's in the reverse way. Children right does not exist, so push the left one, right? The left is 6. Now pop the top element of the stack again into the answer, and again write the childrens of 6. The children of 6 does not exist, so go to the stack, again pop the element 3, right? You pop the element 3 and write the childrens of it. The children of it are 4 and 5, so write in the reverse way. Now you understand why we are writing in reverse way, so that we get access. It works, stack works in LIFO, last in first out. So the last element that you enter into the stack gets outputted first. If you enter the right first and left second, then only you can get access to left first, right? So that you can pop it out first. So left gets pop out, and this is the order that we are following, right? Root, left, right. So in order to get access to left first, you need to push the left second, right? First you need to push the right. That is why we are pushing the right children first and the left children second. Now you have 4. Pop out the element 4, write it out, write the children of 4. Children of 4 does not exist. Again pop out the element 5, write it in the answer. Children of 5 does not exist. And you keep doing it till the stack is empty. Right now clearly the stack is empty, so this will be our answer. 1 2 6 3 4 5. The answer was 1 2 6 3 4 5. Now I will explain it in simple words again. What you do is that you have a tree. Let's say you have a tree, something like, let's say something like this. You have a tree. Now you pick a node, put it into a stack. Let's say this is node 1. You put it into the stack, and from the stack you put it into answer, right? From the stack you put it into answer, pop it out, and write the children of this node in reverse order, so that you get the access of left node fast. So you write 2 3, let's say in this order, 2 and 3, right? So that you can get access to 3 fast. Again pop the top element out from the stack, pop the top element out, write the children in reverse order again. So what you do is you push it into the stack. Step 1 would be pushing it into the stack. Okay, now then what you do is pop it out of the stack. With that, push the 2 childrens if present, right? Again repeat the same process. You push it into the stack, pop it out, and push the 2 children. You keep doing it until and until you don't have until your stack is not empty, right? Till the stack is not empty, you keep doing it. So whatever we did, we'll simply going to write the code for it. First we need to have, the code should be, first we need to have a stack, right? Let's say stack. Now stack would be of the type, let's say tree node, whatever the type would be given, tree node star. So we are actually storing the address in the stack, right? These are not the values that we are storing in the stack. Actually these are the addresses. Values are this one in the answer vector, right? So stack tree node st, let's say. And also we have to have an answer vector. So vector int answer. Now what is the first thing that we did was, the first thing was we push the root of the tree into the stack. So simply do that, push the root of the tree, st dot push, pushing it into the stack, st dot push the root. Now after that, after pushing the one, there will be a chain reaction, right? You keep doing it, you keep pushing and popping out of the stack until and unless the stack is not empty. So write a while condition. Let's say you could have written a for. Let's write a while stack is not empty, st dot empty. While stack is not empty, you keep doing it. Keep doing what? First you let's say first you go to the top element of the stack, right? You go to the top element of the stack, store it in some node, let's say node variable. Now node variable need to be of tree type, tree node, let's say. Go to the top element, store it in the node variable. Then what we are doing was we store the one in the stack, pop it out, and store it in the answer. So do that first, then pop it out, st dot pop, and store it in the answer vector, answer dot pushback. answer dot pushback, what we are pushing back, node, right? Then what we did, after pushing it into the answer, we are storing the childs of that node if present. If null, then don't store it. If present, store the child of the node. First store the right, then the left, so that we get the left access first. So what you do is that you run a if condition. If the node, right, first you need to put the right. If the node right is not equal to null, right? If the node right is not equal to null, and if the node left is not equal to null, right? If the node right is not equal to null, simply push it into the stack, right? Simply push it into the stack, node right. Now remember, these are not values. Okay, there is a little mistake that I did, was in answer we are not pushing the addresses. In answer we are actually pushing the value, right? Node value. Now what we did was, here we push the right node first, then the left node, left, right? And this is over, right? This is the while loop that we have. Now at the end, what we have to do, at the end we have to simply return the answer vector. Now I will give a gist of what I exactly did. Let's say this is the tree. Let's take the simplest tree of 3 nodes, right? This is node 1, 2, 3, and this is the stack that we have. We go to let me change the color. Let's say we have the answer. This is the answer, let's say, and this is the stack. Now first what we did was st.push root. We push the root of the node, root of the tree, into the stack. So our stack has 1 now, right? Now while stack is not empty, take the top element and put it in the node. So we are storing it in the node. Pop it out, pop the top element out, push it into the answer. We pushed it into the answer. Now push the right element first and the left element, followed by the left child. So we push the 2 child, 3 and 2. Again, this is not null. Take out the top element, push it into the stack. Again, this is not null. Take out the top element, push it in the answer, and here you have the pre-order traversal by iterative method using one stack. Now talking about the time and space complexity. Now the time complexity is simply on, because we need to visit at least once to all of these nodes to actually write it into the answer vector, right? We have to visit once, so it will be on complexity. And space complexity will be also on, because we are using an extra space of stack.